Distances in the universe are really and truly mind-boggling. Even within our solar system, it takes light several hours to reach the outer planets, and it takes years and years to travel enormous distances between stars. The state-of-the-art spacecraft today would take tens of thousands of years to get to the star nearest to our system. It may appear that exploring new worlds in those parts will forever be confined to the realm of fantasy. But is it how it is to remain? Of all the planets in the solar system, Mars is the most suitable one for exploration. It regularly approaches our planet, with the distance between us becoming minimal, which is slightly under 56 million kilometers. Light and radio waves travel this far within a matter of 3 minutes. Needless to say, it takes spacecraft a considerably longer time. They have to follow complex trajectories around the system and perform gravity boost maneuvers when in close proximity to planets on their way. The Perseverance Mars rover, for example, traveled to the red planet for slightly less than 7 months. The SpaceX Starship is expected to take considerably less to cover the same distance. But with exact data on this being gleaned admittedly slowly, nothing definite can at this point be said about the duration of the planned expedition to Mars. Traveling to other stars is still more difficult. Even light, whose speed is known to equal slightly less than 300,000 kilometers per second, needs over 4 years to reach Proxima Centauri, the closest star to us outside our system. Incidentally, it would take the most advanced spaceship today to finish this same journey around 40,000 years. Come to that, even this figure is rather optimistic, because there is the sun's gravitational influence to be reckoned with. A spacecraft will have to accelerate to speeds upwards of 47 kilometers per second, which will require incredibly large amounts of fuel, or else rather time-consuming, although elaborately planned, gravity boost maneuvers on the way. Unfortunately, expectations of this kind of speed still border on fantasy. The fastest spacecraft today is the Parker Solar Probe, launched by NASA in 2018. Its speed reached as high as 147 kilometers per second in April 2021. In addition, after a number of upcoming gravity boosts planned for the nearest years, the probe will be capable of accelerating to a staggering 194 kilometers per second. In other words, approximately 700,000 kilometers per hour. Regrettably, the probe is moving to meet the sun rather than escape from it, and it cannot use the developed speed to exit our system. Most spacecraft, however, do not exceed a speed of a measly 11 kilometers per second. This is quite enough to send a spaceship into orbit or even reach the moon. As for getting as far as other objects in the solar system, a much more potent acceleration is called for. Unfortunately, even today's most powerful engines would not make for a fast flight. Speaking about interplanetary space probes exploring the outskirts of our system, it takes them decades to reach their destinations. The snag is that even the best modern rocket engines have a number of some major drawbacks. The payload mass of the rocket's body accounts for just a few percent of its overall mass. The specific impulse, on the other hand, has reached its technological limit. If objects in the solar system can be reached by such rockets, at least in theory, traveling to stars definitely requires new ways. It goes without saying that there are ways to boost the speed of a spaceship. With some of them appearing ridiculously incredible, others are actively resorted to even now. To mention but one, iron thrusters, for example. By accelerating in an electrostatic field, charged particles give their impulse to the spacecraft. Even today, iron thrusters' performance shows to be 70 times higher than that of chemical-powered ones. This means that their use could not only boost spacecraft better, but also allow their payload mass to be higher. Unfortunately enough, these thrusters are not powerful enough to take care of a spaceship's liftoff from the Earth yet. But incidentally, they've been used since the 1970s on satellites and orbital stations for maneuvering and orbital adjustments. Another approach implies abandoning the idea of jet propulsion completely. Instead, the pressure of light can be used. By capturing a stream of photons emitted by our sun, a solar sail is capable of boosting the speed of a spacecraft to hundreds of kilometers per second, and that almost without using any energy. Alternatively, solar wind may be captured instead of light. In this case, the sail is called an electric sail. Nevertheless, it is impossible to lift off the face of the Earth or any other planet by using this sail. Of course, other ways of producing a thrust may be used to enter space with a sail deployed later on. But this doesn't take care of the following problem. When a long distance away from any star, this engine is quite ineffective. The point is that the density of a stream of photons in interstellar space is much lower than in a star's environs. That is why it is quite hard for a spaceship like that to travel between stars. By the same token, the sail itself has to be made of materials that are both exceptionally tough and light. Probably graphene film or other scientific inventions will help develop these extra economical, although not very powerful spacecraft. Research in this field might produce a photon-powered starship. A powerful source of light could be created that would exert a force on a gigantic parabolic mirror, and a small amount of antimatter could create the necessary beam. This concept admittedly resembles something one could come across in science fiction. In today's stage of technological development, mankind isn't capable of designing either a mirror of this kind or a powerful enough source of light. Another way to produce thrust is to use the power of nuclear decay. As specified in a US project dating back to the middle of last century, a spaceship equipped with a nuclear fusion-based impulse engine could reach Alpha Centauri in 130 years' time. It would accelerate following a series of nuclear explosions around 1 kiloton each. The atomic shockwave would bounce off a solid thermal resistance shield and easily hurl the spacecraft through and out of the Earth's atmosphere, boosting it to incredible speeds. The major drawback for going ahead with this kind of spacecraft was concerns about radioactive pollution of the launch site, as well as difficulties in producing an elaborate tappet. It is no easy matter to design a shield that would withstand a series of nuclear explosions, even though not very powerful ones. In the end, the project on the construction of an impulse engine based on nuclear fusion was deemed to have no chance of success, and all research in the field was stopped. However, this doesn't mean that fission energy cannot be used for space travel. In the most elementary project of a nuclear engine, hydrogen is funneled through the active zone of a nuclear reactor, which is made of tough uranium rods. The heat emitted in the process of nuclear decay makes the gas reach high temperatures. After that, it is ejected from nozzles, thus propelling the spacecraft forward. This kind of engine is known as solid core, and excitingly, it is possible to construct one even at our current stage of technological development. Besides, the solid core nuclear thermal thruster specific impulse is at least twice as high as that of today's chemical powered ones. The temperature of the active zone of a solid core nuclear thermal rocket mustn't exceed 3,000 degrees Celsius on account of the destruction hazard of the construction elements. On increasing the temperature up to as high as around 25,000 degrees Celsius, the inner part of the reactor will crumple to turn into a cloud of red-hot radioactive magma. The efficiency of the engine, meanwhile, will be boosted dozens of times. This kind of engine is gas core. It may not only reach Mars as quickly as just in a few weeks' time, but may break away from the Sun's gravitational influence and, in theory, get as far as other stellar systems, keeping the radioactive plasma red-hot calls for complex technical solutions. Not a single kind of material is able to stop a plasma cloud as hot as tens of thousands of degrees Celsius. Only extremely powerful electromagnetic fields of specific configurations would be capable of that. Technologies necessary to achieve this are being developed even at this moment. These technologies are also needed to develop a still more powerful engine, which would be powered by thermonuclear energy. Thermonuclear synthesis doesn't require heavy elements, which are difficult to come by in space. Instead, hydrogen is used, the most widespread element in the universe. Besides, much more energy is released in a thermonuclear reaction than during decay of heavy elements. This kind of thruster is estimated to be able to boost the spacecraft's speeds up to 10,000 times more efficiently than the engines we have today, which means that getting to closest stars may take far less time, just a few decades. The Bussard ramjet is a hypothetical rocket project, which is a modification of these fusion rockets. It is powered by a thermonuclear jet, and at its front there is a huge ram scoop. The ramjet is supposed to collect hydrogen in the interstellar medium and use it as fuel or working propellant fluid. When reaching a certain speed, the ramjet is supposed to collect as much gas as it uses to boost itself. This makes the Bussard ramjet pretty much autonomous. Still, all these engines are incapable of reaching even a tenth of the speed of light reasonably fast. That is why, at the end of last century, the Mexican physicist Miguel Alcubierre put forward a rather presumptuous hypothesis. The basis of it is this: if it is not possible to travel in space at superluminal speeds, then space itself may be made to move. According to Alcubierre's hypothesis, by using a warp drive, space could be made to contract in front of the spacecraft and expand behind it. To achieve this, the so-called exotic matter would be needed. Indeed, this matter would have rather specific properties like negative energy density. It may theoretically exist, but it hasn't been experimentally discovered yet. For a long time, Alcubierre's hypothesis didn't used to be taken seriously, first and foremost on account of the necessity of exotic matter and a lack of experimental confirmations. In all probability, it would have remained unconfirmed if it were not for some hopeful news in the past several months. Firstly, the German astrophysicist Erich Lenz developed a theory where no exotic energy is needed to create the Alcubierre drive or the warp bubble. Instead, Lenz suggested forming it with a single wave, created with the help of a special kind of plasma, referred to as a soliton. This special wave is capable of traveling large distances without losing either its impulse or shape. No exotic matter is needed to create such perturbations in space. Still, the amounts of energy necessary to set the wave rolling are extremely large. It would take annihilating dozens of Jupiters for the spacecraft to get to Proxima, the closest star to the solar system. However, Erich Lenz claims that energy consumption could be reduced 30 to 60 times, and he is currently busy with the calculations. Another piece of latest news in the field is from physicists Alexei Bobrik and Gianni Martire, working in New York, who adapted the theory of their colleague from Mexico and dropped the idea of exceeding the speed of light. The decision to operate at sublight speeds takes care of a number of paradoxes otherwise uncounted, and in theory allows for accelerating to extremely high speeds in the future. Moreover, calculations show that the energy needed to create the bubble has dropped by substantial margin and equals the amount produced by annihilation of one Earth mass. The scientific progress of mankind grows by the day. What would appear to be a figment of imagination would have become common today. Incredible suggestions turn into applicable prototypes and then become part of our daily life. Everyday dreams about visiting stars assume more realistic shapes. For all we know, we will soon witness humans settling on new planets. And in the meantime, stay with Cosmo and feel free to support our project by hitting the like button. Let's keep in touch.